Look up at the night sky, and you're seeing more than just stars. You're seeing history. Every point of light is a message from the past, telling the story of a cosmos that's been stretching, evolving, and expanding for nearly 14 billion years. And at the heart of that grand cosmic story lies one number, so critical to our understanding of the universe that it's been called the Holy Grail of modern cosmology, the Hubble Constant. It tells us how fast the universe is growing, how quickly galaxies are racing away from one another, and ultimately, how old everything truly is. For decades, scientists have worked to pin down this fundamental value, believing it would unlock the deepest secrets of space and time. But something unexpected has happened, a mystery so strange and so stubborn that it has shaken the very foundations of physics. This is the Hubble tension, a puzzling and persistent discrepancy in how we measure the expansion of the universe. On one hand, we have meticulous observations of the early universe, the faint afterglow of the Big Bang, pointing to one value. On the other, measurements taken from nearby stars, supernovae, and other cosmic markers tell a different story. They don't match, they should, but they don't, and that tiny gap between them has sparked one of the greatest scientific detective stories of our time. It isn't just a small error or a rounding issue. It's a rift, a cosmic disagreement that hints we might be missing something profound about the laws that govern reality itself. In this video, we're going to explore 25 reasons why this tension has left some of the brightest minds in astronomy both baffled and thrilled. We'll journey from the earliest moments of the cosmos to the cutting edge of modern astrophysics, digging into everything from dark energy and neutrinos to the possibility of entirely new physics waiting to be discovered. This isn't just about numbers that don't add up, it's about a mystery that could redefine our place in the universe. So settle in. What you're about to hear may change how you see the night sky forever. The very first reason this cosmic puzzle is so profound lies in a fundamental split in how we observe the universe. We are essentially looking at two different chapters of the same cosmic story, and they seem to be telling us two subtly different versions of events. On one side, we have the pristine, ancient light from the universe's infancy. On the other, we have the brilliant, modern beacons from our own cosmic neighborhood. And the numbers they give us for the expansion rate simply refuse to agree. Let's start with the early universe, the opening chapter. To read this part of the story, scientists use the most important fossil in all of cosmology, the cosmic microwave background, or CMB. This is the faint, cold afterglow of the Big Bang itself, a snapshot of the universe when it was just 380,000 years old. At that moment, the hot, dense soup of particles finally cooled enough for light to travel freely across space for the first time. That light has been journeying for nearly 14 billion years, and it carries with it an immense amount of information about the conditions of the young cosmos. Incredibly precise missions like the Planck satellite have mapped the tiny temperature fluctuations in this background radiation with stunning detail. By analyzing these patterns, scientists can work backwards, using our well-tested theories of physics to calculate what the Hubble constant must have been to create the universe we see today. It's like finding a detailed blueprint of a building, and from that alone being able to calculate exactly how fast the construction crew must have been working. This method gives us a very specific, highly trusted value for the expansion rate. Now, let's jump to the present day, the latest chapter. To measure the expansion rate now, astronomers use what are called the cosmic distance ladder. This isn't one single tool, but a series of interconnected steps that allow us to measure distances to faraway galaxies with remarkable precision. The first crucial rung on this ladder is built with Cepheid variable stars. These are special stars that pulsate with a rhythm that is directly tied to their true brightness. By measuring how fast they pulse, we know their intrinsic brightness. Then, by comparing that known brightness to how dim they appear from Earth, we can calculate their distance incredibly accurately. It's like knowing the exact wattage of a light bulb. By seeing how faint it looks, you can tell exactly how far away it is. The next, even more powerful rung uses type 1 as supernova. These are colossal stellar explosions that always peak at the same known brightness. They are so brilliant they can be seen across billions of light years, acting as the ultimate standard candles. By measuring the distances to these supernovae and then seeing how fast their host galaxies are moving away from us, their redshift scientists can directly calculate the Hubble constant in our modern era. And here is the heart of the conflict. These two methods, each incredibly robust and precise in their own right, are giving us different answers. The Planck measurements of the ancient CMB suggest a Hubble constant of about 67.4 kilometers per second per megaparsec. Meanwhile, the measurements from supernova and Cepheids point to a faster expansion rate of around 73 kilometers per second per megaparsec. That gap of about 5 or 6 units might seem small, but the precision of these measurements is so exquisite that the chance this is a simple error is astronomically small, less than 1 in a million. It's not just a minor discrepancy, it's a direct contradiction. The early universe blueprint suggests one speed of construction, but when we look at the modern building itself, it appears to have been built significantly faster. This isn't just a tension between two numbers, it's a tension between two completely different eras of cosmic history, implying that our understanding of the physics connecting the past to the present might be fundamentally incomplete. What makes this discrepancy so compelling and so deeply troubling for cosmologists is the sheer, unshakable confidence they have in the data from the Planck satellite. This isn't a rough estimate or a fuzzy reading. It is arguably the most precise cosmological data set ever collected. The Planck mission was designed to map the cosmic microwave background with a level of detail that was almost unimaginable just a generation ago. Orbiting a point in space nearly 1 million miles from Earth, it spent years meticulously scanning the entire sky, measuring the faint whispers of heat left over from the Big Bang. Its instruments were so sensitive they could detect temperature variations in this ancient light of just 1/1,000,000th of a degree. The map it produced is exquisitely detailed, revealing the subtle lumps and bumps in the early universe, the seeds that would one day grow into entire galaxies and galaxy clusters. From this incredibly rich tapestry of data, scientists can extract the fundamental parameters of our cosmos with breathtaking precision. They use a powerful, well-established model of the universe known as the lambda-cold dark matter model. Think of this model as the ultimate cosmic recipe, with ingredients like ordinary matter, dark matter, and dark energy, all mixed in specific proportions. By feeding the Planck data into this model, we can determine those proportions with extraordinary accuracy. The Hubble constant isn't a standalone number in this process. It's deeply intertwined with everything else. It's one of the 6 key parameters that the model solves for simultaneously. The result is a value for the expansion rate that is not just a number, but a number with remarkably tiny error bars. The Planck collaboration reported a Hubble constant of 67.36, plus or minus 0.54. kilometers per second per megaparsec. This means they are about 99.9999% certain that the true value lies within that incredibly narrow range. This precision is what transforms a simple disagreement into a full-blown crisis. When one of your measurements is this precise and this confident, it becomes extremely difficult to wave away the discrepancy as a simple mistake or an error in calibration. It's like using a world-class, laser-calibrated ruler to meticulously measure a piece of wood and finding it is exactly 10.000 centimeters long. Then you use a different but also highly accurate measuring tape and it insists the same piece of wood is 10.5 centimeters. You check and recheck both tools. The laser ruler is functioning perfectly and its calibration certificates are impeccable. the measuring tape also appears to be correct, yet they stubbornly disagree. The precision of the first measurement makes the disagreement undeniable and deeply puzzling. You are forced to confront a terrifying possibility. Perhaps the rules of measurement themselves are different than you thought. In cosmology, the Planck data is that laser-calibrated ruler. Its incredible precision makes the tension not just a curiosity, but a profound clue that we might be missing a fundamental ingredient in our cosmic recipe. While the Planck data gives us an exquisitely detailed view of the universe's infancy, the other side of this cosmic disagreement comes from a completely different, yet equally impressive feat of astronomical engineering, building a precise measuring tape for the modern cosmos. This technique is poetically known as the cosmic distance ladder, and its reliability is what makes the Hubble tension so impossible to ignore. Imagine trying to measure the distance to a mountain on the horizon. You wouldn't use a single tool. You might start with a ruler for something close, use that to calibrate a rangefinder for a mid-range object, and then use that to finally gauge the faraway peak. Astronomers do the exact same thing, but on a galactic scale. They construct their ladder one confident rung at a time, moving from nearby stars to the vast emptiness between galaxies. The entire process hinges on finding what are called standard candles, celestial objects with a known, predictable brightness. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its exact distance. It's the cosmic equivalent of knowing a 100-watt light bulb is in a lamp. The fainter it looks, the farther away you know it must be. The first and most crucial rung of this ladder is built with a special class of stars known as Cepheid variables. Their discovery was a cornerstone of modern astronomy. These stars rhythmically pulse, growing brighter and dimmer over periods that can range from days to months. In the early 20th century, the brilliant astronomer Henrietta Leavitt made a groundbreaking connection while studying these stars. The longer the pulsation period, the higher the star's true intrinsic brightness. This period luminosity relationship was a revolution. It meant that by simply timing the heartbeat of a Cepheid variable, an astronomer could immediately know its true power output. This turned them into the first reliable standard candles for measuring distances beyond our own solar neighborhood. By finding Cepheids in a relatively nearby galaxy, we can pin down that galaxy's distance with great confidence. They provide the solid, local foundation upon which the entire rest of the ladder is built. But Cepheids, as powerful as they are, have their limits. We can only spot them out to a certain distance before they become too faint to see clearly. To reach across the vast cosmic voids and measure the expansion of the universe itself, we need a brighter beacon. This is where the top rung of the ladder comes in, Type 1, a supernova. These are among the most violent and energetic explosions in the universe. They occur in a specific binary star system where a white dwarf star steals material from a companion until it reaches a critical mass and detonates in a thermonuclear blast. The key is that this critical mass is always the same, which means the peak brightness of every single Type 1 a supernova is virtually identical. They are the ultimate standard candle, shining with the brilliance of 5 billion suns, visible clear across the observable universe. Here's where the ladder connects. Astronomers use the Cepheid variables to precisely measure the distance to galaxies that are relatively close and have recently hosted a Type 1 a supernova. This carefully calibrates the true peak brightness of these supernovae. Once that calibration is locked in, they can then find these supernovae in galaxies that are incredibly far away. They measure how dim these distant supernovae appear, which gives them the distance to those far-off galaxies. Finally, they measure the redshift of the light from those same galaxies, how much the expansion of the universe has stretched their light toward the red end of the spectrum, to see how fast they are receding from us. By comparing the distance to the recession velocity for many galaxies, they can directly calculate the Hubble constant here and now. This entire meticulous process, led by teams like the one working with the Hubble Space Telescope, which is ironically named for the man who first discovered the expansion, has yielded a value of around 73 kilometers per second per megaparsec. The confidence in this local measurement is immense. Every potential source of error has been scrutinized, tested, and accounted for. Could dust be dimming the light of the Cepheids and supernova, making them seem farther away than they are? Teams have observed them at multiple wavelengths to correct for this. Are there quirks in the physics of the supernova themselves? Decades of study suggest they are remarkably uniform. This isn't one single measurement, it's a chain of thousands of interconnected, cross-checked observations. The local distance ladder is a masterpiece of practical astronomy built over a century of painstaking work. And its result is clear, consistent, and refuses to align with the story told by the primordial light of the CMB. We are left with two impeccable measuring tools, each constructed with flawless logic and breathtaking precision, each providing a confident answer, and yet those answers are undeniably different. This is the core of the mystery, and it strongly suggests the problem isn't with our measurements, but with our understanding of the universe they are measuring. Of course, this stubborn disagreement between two impeccable methods forces us to ask a very uncomfortable but necessary question. Could someone simply be making a mistake? What if the problem isn't with the cosmos but with us? This leads us to the fourth and perhaps most humbling reason the Hubble tension is so puzzling: the persistent, nagging possibility of systematic errors. A systematic error isn't just a random mistake, it's a consistent, hidden flaw in the measurement process itself. It could be a subtle miscalibration in a telescope's instruments, a blind spot in our data analysis, or an incorrect assumption about the physics of the objects we're observing. The frightening thing about such errors is their consistency. They push every single measurement in the same wrong direction, creating a result that appears precise and confident but is fundamentally biased. Given the monumental stakes, scientists have turned into their own most ruthless critics, launching exhaustive campaigns to hunt for any hidden flaws. Teams working on the local distance ladder have scrutinized every single rung. Could there be something we don't understand about Cepheid variables? Perhaps their period luminosity relationship isn't as universal as we thought. Maybe it changes slightly depending on the chemical composition of the star or its environment. Researchers have obsessively measured Cepheids in different types of galaxies, at different wavelengths of light, searching for any such effect. So far, while tiny adjustments have been made, no found systematic effect is large enough to close the gap. The same intense scrutiny has been applied to Type 1a supernova. Is it possible that these standard candles aren't perfectly standard? Could the properties of the white dwarf or its companion star cause slight variations in the peak brightness? Decades of data from thousands of supernovas suggest they are remarkably reliable, and any minor variations are well understood and accounted for. Another major concern is interstellar dust. Our galaxy and others are filled with tiny grains that can dim and redden starlight, making a supernova appear farther away than it truly is, which would artificially inflate the measured expansion rate. Astronomers have attacked this problem by observing these objects in multiple wavelengths, from the ultraviolet to the infrared, allowing them to precisely measure and subtract the effects of dust. Yet, even after these meticulous corrections, the higher expansion rate remains. On the other side of the divide, the Planck team and other CMB researchers have been equally rigorous in their self-examination. Could there be an unaccounted-for source of interference contaminating the pristine signal of the ancient light? The team has painstakingly modeled and subtracted the faint foreground emissions from our own Milky Way galaxy and other nearby sources. They have analyzed their data using multiple, independent methods to check for biases introduced by their analysis techniques. The results are robust. The parameters of the universe that pop out of the CMB data are all deeply intertwined. Changing one to try and force a higher Hubble constant would immediately throw other well-measured values, like the amount of dark matter or the clumpiness of the early universe, into conflict with independent observations. The model itself is a house of cards, but it's a remarkably stable one. Pulling one card out to solve the tension causes the whole structure to wobble. The truly baffling outcome of this global detective hunt is that both methods have emerged looking stronger, not weaker. Each team, in trying to disprove the other, has only reinforced the validity of their own results by eliminating one potential error after another. They haven't found a smoking gun, a single glaring error that explains the discrepancy. Instead, they've been left with a quiet confidence in their own numbers and a growing sense of unease about what the disagreement implies. The possibility of a hidden systematic error can never be entirely eliminated, of course, but the longer the tension persists despite this relentless scrutiny, the more it points away from a simple human error and toward something far more exciting. A crack in the edifice of our physical understanding, waiting for a new generation of scientists to pry it open. And this brings us to the fifth and most exhilarating reason the Hubble tension has captivated the scientific community: the tantalizing possibility that it is not a mistake at all, but our first real glimpse of physics beyond our current understanding. When two of the most rigorously tested measurements in all of science refuse to agree, even after every conceivable error has been hunted down, you are eventually forced to consider a revolutionary idea. Perhaps the model itself is incomplete. The magnificent edifice of modern cosmology, known as the lambda cold dark matter model, has been stunningly successful at describing the universe we see. But the Hubble tension might be the first observable crack in its foundation, a sign that we need to add a new, unexpected ingredient to our cosmic recipe. Think of the lambda CDM model as a perfectly tuned engine that takes the initial conditions of the Big Bang and runs them forward 14 billion years to predict the universe of today. For the most part, this engine runs beautifully, but the Hubble tension is like a persistent, faint knocking sound that the mechanics can't eliminate. They've checked every known part, tightened every bolt, and replaced every sensor, yet the knock remains. The only logical conclusion is that there's a part in the engine we didn't even know was there. This new physics isn't about overturning Einstein's theory of relativity or quantum mechanics. Those remain rock solid. Instead, it's about discovering new components within that existing framework, new particles, new fields, or new properties of the dark universe that we simply haven't accounted for yet. One of the most discussed ideas involves an early form of dark energy. We know that dark energy is the mysterious force causing the universe's expansion to accelerate today. But what if a different version of it also briefly flickered on during the universe's first few 100,000 years? This phenomenon, often called early dark energy, would have acted as a temporary booster rocket during the cosmos's infancy. It would have slightly altered how sound waves traveled through the primordial plasma, effectively changing the cosmic blueprint that the Planck satellite measures. This would mean that when we use that blueprint to calculate what the Hubble constant should be today, we get a slightly lower number because our calculation didn't account for that extra early push. Meanwhile, the local distance ladder measures the expansion rate directly, catching the full, unedited result of that historical boost, hence the higher value. It's an elegant solution that tweaks the early universe just enough to make both measurements correct. Other theories look at the dark matter that makes up most of the universe's mass. What if dark matter isn't entirely cold and passive? Perhaps a small fraction of it possesses a tiny amount of interaction, allowing it to slow down and clump ever so slightly differently over cosmic time. Or maybe dark matter itself can decay into other, lighter particles, injecting energy into the expansion history at a key moment and gently altering the rate. There are even more exotic proposals, such as the existence of previously unknown types of neutrinos often called sterile neutrinos. that are far heavier than the ones we know and that would have influenced the gravitational pull of the early universe. Each of these ideas is a potential key to the puzzle, a way to nudge the theoretical prediction from the early universe upward to meet the local measurement without breaking all the other things the model gets right. The beauty of this mystery is that it is a true scientific frontier. It's not just about resolving a numerical discrepancy, it's a guided hunt. The Hubble tension tells us that something is missing, and it even tells us when its effects must have been most pronounced in the dark ages between the release of the CMB and the formation of the first stars. This gives theorists a specific sandbox in which to play, inventing and testing new models against a very precise constraint. It transforms the tension from a problem into a beacon, shining a light on the path toward a deeper, more complete theory of everything. The excitement within the physics community is palpable because this isn't an abstract philosophical debate. It's a concrete anomaly that next-generation telescopes, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, are actively designed to investigate. They will peer into that critical era, searching for the faintest whispers of evidence that could confirm we are on the verge of a discovery that will rewrite the textbooks. This brings us to a force so enigmatic that its very nature is the biggest unsolved problem in physics: dark energy, and it is directly at the heart of the Hubble tension. In our standard model of cosmology, dark energy is represented by the Greek letter lambda, and it is treated as a constant, a fixed, unchanging property of empty space itself that exerts a gentle, repulsive pressure, causing the expansion of the universe to accelerate. This simple cosmological constant has been a brilliant fit for a vast array of data. But what if dark energy isn't so simple? The Hubble tension is forcing scientists to ask a profound question: could dark energy be evolving? The core of the issue lies in how the expansion rate has changed over the lifetime of the cosmos. The Hubble constant isn't actually a constant in time, it's the expansion rate measured right now. The real story is how that rate has been shaped by the tug-of-war between the gravitational pull of all the matter in the universe trying to slow things down, and the push of dark energy trying to speed things up. In the standard model, dark energy is a very recent dominant player. For the first 9 billion years, gravity was winning and the expansion was gradually slowing. Then, around 5 billion years ago, dark energy took over and the expansion began to accelerate. The value we measure locally with supernova is a direct snapshot of this current accelerating era. But the early universe measurement from the CMB is a prediction based on running the standard model forward. It assumes that dark energy has always behaved as this simple, constant force. The tension suggests that this assumption might be wrong. Perhaps dark energy's strength has not been constant. Maybe it was stronger in the past, or maybe it's growing stronger now at a different rate than we thought. Even a small change in the behavior of dark energy would have a ripple effect through the entire cosmic timeline, altering the predicted connection between the ancient universe and the modern one. Consider this analogy. Imagine tracking the growth of a child. You have a detailed baby picture, the CMB, and a sophisticated model that predicts how fast they should grow based on a steady diet and exercise. You predict that today, as an adult, they should be 5 feet 10 inches tall, but when you actually meet them, they stand 6 feet 2. The model is wrong. The discrepancy forces you to reconsider your assumptions. Maybe their nutrition was different than you thought, or perhaps they had a growth spurt you didn't account for. In cosmology, dark energy is that nutritional history. The Hubble tension is the height discrepancy telling us that our model of its diet, the simple, constant lambda, might be insufficient. This opens the door to thrilling possibilities. Perhaps dark energy is not a property of vacuum space but a dynamic field, often called quintessence, that can change density and strength over time. If this field was slightly more potent in the universe's first few 100,000 years, a concept known as early dark energy, it would have given the expansion a tiny extra nudge, modifying the sound waves imprinted on the CMB. This would mean the Planck satellite's blueprint is for a universe that received that early boost, so when we calculate forward assuming constant dark energy, we underestimate what the present-day expansion rate should be. The local measurements would then be correct, capturing the true result of that historical push. Alternatively, maybe dark energy is strengthening in the present epoch, causing a more recent and sharper acceleration than the standard model allows. This would also drive a wedge between the predicted and observed values of the Hubble constant. The implications are staggering. We may be on the verge of discovering that the force dominating the fate of our cosmos is not a static background but an active, evolving participant in its history. A discovery that would fundamentally reshape our understanding of everything from the Big Bang to the ultimate fate of the universe. But to truly grasp the scale of this mystery, we must turn our attention to the invisible scaffolding of the cosmos, dark matter. This enigmatic substance makes up about 85% of all the matter in the universe. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. We only know it's there because of its immense gravitational pull, which dictates how galaxies spin and how the largest structures in the universe form. In our standard cosmological model, this dark matter is assumed to be cold and collisionless. Cold meaning it moved relatively slowly in the early universe, allowing it to clump together and form the gravitational wells that galaxies would later form inside. Collisionless meaning its particles barely interact with each other or with normal matter. They just pass right through everything, governed solely by gravity. This simple, minimal description has worked incredibly well, but the Hubble tension is forcing us to ask, what if dark matter is a little more complicated? The discrepancy in the expansion rate could be a subtle signal that dark matter's influence on the cosmos isn't as straightforward as a simple gravitational tug. Perhaps a small fraction of it interacts with itself through some unknown force beyond gravity. If dark matter particles could bump into each other, even very rarely, it would change how they behave. In the early universe, this self-interaction would create a slight pressure that resists gravity's pull, preventing dark matter from clumping together as efficiently. This would subtly alter the pattern of sound waves frozen into the cosmic microwave background. The Planck satellite's measurement of that pattern is what leads to its lower prediction for the Hubble constant. If the early universe was actually slightly less clumpy because of self-interacting dark matter, then our standard interpretation of the CMB data would be slightly off. Correcting for this previously unknown interaction could nudge the predicted expansion rate upward, potentially closing the gap with the local measurements. Another fascinating possibility involves dark matter decaying. What if over billions of years, some dark matter particles have slowly transformed into lighter, more energetic particles? This process would inject additional energy into the universe, effectively giving the expansion an extra little kick. The local distance ladder, which measures the expansion in the relatively recent cosmic past, would capture the effect of this ongoing energy injection, resulting in a higher measured value. Meanwhile, the CMB prediction, which is based on the initial conditions of the universe, wouldn't account for this late-time boost. It's a cosmic sleight of hand where the rules of the game appear to change subtly over time, with dark matter itself slowly evolving and influencing the rate of expansion in ways our standard models never anticipated. This isn't just wild speculation, it's a direct response to a clear data anomaly. The Hubble tension acts like a forensic clue, pointing investigators toward a specific moment in cosmic history. The fact that the early and late universes don't perfectly align tells us that if there is new physics in dark matter, its effects must have been most pronounced in the vast, dark ages between the release of the CMB and the formation of the first stars. This is the era when dark matter reigned supreme before dark energy took over. A small change in its behavior during this critical period could ripple forward through time, creating the discrepancy we observe today. By considering that dark matter might have a richer physics than mere gravity, we open the door to a universe that is far more dynamic and interconnected than we ever imagined. Now we venture into the realm of the incredibly small to solve a problem of cosmic proportions. The eighth reason the Hubble tension is so puzzling involves the most elusive and ghostly particles in the universe, neutrinos. Trillions of these subatomic phantoms are streaming through your body every second, born from the hearts of stars, the violence of supernovae, and even the aftermath of the Big Bang itself. They barely interact with anything, making them incredibly difficult to study, yet they are fundamental players in the cosmic story. Their potential role in this mystery highlights a stunning truth. The largest-scale properties of our universe can be exquisitely sensitive to the behavior of the smallest known particles. To understand how neutrinos could be involved, we need to go back to the first second after the Big Bang. The universe was an unimaginably dense and hot soup of fundamental particles. Among them were vast numbers of neutrinos, so many that they formed a dominant background sea, much like the cosmic microwave background but for matter instead of light. These are known as relic neutrinos, and they are still everywhere around us today, though their energy has been diluted to almost nothing by the expansion of space. In our standard cosmological model, these neutrinos are treated as very light, fast-moving particles that stream freely through the universe, subtly influencing how structures form through their gravity and their kinetic energy. But what if our standard assumptions about them are just a little bit wrong? The key lies in how these light particles affect the critical moment when the first atomic nuclei formed, a process called Big Bang nucleosynthesis, and later the release of the CMB. Heavier, slower-moving neutrinos would have a greater gravitational effect. If relic neutrinos were more massive than we currently believe, or if there were more types or flavors of them than the three we know about, it would change the gravitational dynamics of the early universe. More mass means more gravity pulling inward, which generally works to slow down the expansion. However, the effect is more nuanced. These particles also contribute pressure and energy density to the cosmic fluid. If they were slightly heavier, they would have transitioned from behaving like radiation to behaving more like matter at a slightly different time. This shift in timing can alter the precise clockwork of the early universe, changing how quickly it expanded during those first critical moments. This seemingly minor adjustment has a direct impact on the sound waves imprinted in the CMB. The Planck satellite measures the size of these frozen waves to infer the universe's expansion history. If the properties of neutrinos meant the universe expanded just a fraction of a percent faster or slower during those first few 100,000 years, the apparent size of those sound waves would be different. Our current models, which use the best estimates of neutrino properties from particle physics experiments, produce one prediction for the Hubble constant. But if those neutrino properties are incorrect, our interpretation of the CMB data would be based on a flawed premise. Correcting for the true nature of neutrinos could therefore shift the predicted value of the Hubble constant from the early universe, potentially bringing it into line with the value we measure locally. Furthermore, the potential existence of a hypothetical fourth type of neutrino, often called a sterile neutrino, adds another layer of intrigue. Unlike the three known neutrinos, which do interact via the weak nuclear force, a sterile neutrino would interact only through gravity, making it even more ghostly and impossible to detect with current particle physics experiments. If such a particle existed and had a specific mass, it would have been a significant component of the early universe's energy budget. Its presence would have provided an extra source of gravity and radiation-like energy, subtly changing the rate of expansion during the epoch when the CMB was formed. Once again, this would mean that the blueprint we think we're reading from the Planck data is based on an incomplete list of ingredients. The local measurement of the expansion rate would be the true value, while the early universe prediction would be a miscalculation based on our ignorance of these elusive particles. The Hubble tension, therefore, might not be an error in observation but a magnificent signpost pointing us toward a deeper understanding of the neutrino, one of the most mysterious and abundant particles in existence. This brings us to a concept that is absolutely central to the entire mystery, a cosmic measuring stick frozen in time, the sound horizon scale. To understand why the Hubble tension is so stubborn, we must dive into the physics of the very early universe and look at the most important fossil record we have, not just its existence, but the precise size of the patterns written within it. The sound horizon is the fundamental standard ruler used to calibrate the entire early universe, and the possibility that we might be misinterpreting its length is a profound and compelling reason for the discrepancy. Let's rewind the cosmos to its first few 100,000 years. The universe was not silent, it was a roaring, seething ocean of plasma, a hot and dense soup of protons, electrons, and light. In this environment, particles were constantly interacting, but crucially, photons, particles of light, were tightly coupled to the electrically charged electrons and protons. This coupling created a fascinating phenomenon, pressure waves. Imagine a vast cosmic bell being rung. Any tiny fluctuation in density would create a spherical pressure wave that would radiate outward through this primordial soup. The key ingredient here is the speed of sound. In any medium, the speed at which a pressure wave travels depends on the properties of that medium. In this hot plasma, the speed of sound was incredibly fast, a significant fraction of the speed of light itself. Now, fast forward to that critical moment of recombination, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the photons were set free. They decoupled from the matter and began their journey across the universe, which we now detect as the cosmic microwave background. But in that instant of decoupling, a snapshot was taken. The ringing of that cosmic bell was frozen in place. The pressure waves that were racing outward at that exact moment were imprinted onto the CMB as a very specific pattern of hot and cold spots. The distance that one of these sound waves could travel from the Big Bang until the moment of recombination is known as the sound horizon scale. This distance became a fixed standard ruler etched onto the fabric of the universe. This is where the magic happens for cosmologists. By meticulously measuring the apparent angular size of these frozen sound waves on the sky, how big they look to us, the Planck satellite can calculate the actual physical size of that sound horizon ruler. It's basic trigonometry. If you know the size of an object and how big it appears, you can calculate its distance. From there, scientists can work backwards to determine all the fundamental parameters of the universe, including the Hubble constant. The entire edifice of our early universe prediction rests on the assumption that we know the precise length of this cosmic ruler. But what if the ruler itself is not the length we think it is? This is the crux of the ninth reason for the tension. The Hubble tension could be screaming at us that the sound horizon scale was actually slightly different than our standard models assume. How could that be? It all comes down to the speed of sound in that primordial plasma. Our models make a very specific calculation for how fast those pressure waves were moving. But that speed depends on the ingredients and conditions of the early universe. If there was an unknown component or a subtle interaction at play before recombination, something that altered the density or the pressure of that primordial soup, it would have directly changed the speed of sound. For instance, consider the earlier idea of early dark energy. If this exotic energy field was present, even for a brief period, it would have contributed additional energy density to the universe without participating in the pressure waves. This would have effectively made the cosmic fluid a little more sluggish, reducing the speed of sound. A lower speed of sound means that those pressure waves couldn't travel as far in the same amount of time. The sound horizon, our fundamental ruler, would be shorter. Now, when the Planck satellite measures the angular size of these frozen waves, it would see patterns that appear to be a certain size. If the actual physical ruler was shorter than we thought, then to make those patterns appear the same size on the sky, the universe must be closer to us. This would imply a larger Hubble constant to make the geometry work. In other words, a shorter sound horizon would force the predicted expansion rate to be higher, potentially aligning it with the local measurements. This is the elegant and subtle shift in thinking that the tension demands. We've been assuming the ruler is a fixed known length based on our standard physics. But the disagreement between past and present suggests that the ruler might have been malleable. The early universe might have contained physics that slightly modified the properties of the primordial plasma, changing the dynamics of those first pressure waves and therefore the fundamental scale we use to measure everything. It transforms the Hubble tension from a problem of measurement into a potential discovery about the very conditions of the infant cosmos, a hint that the universe's first moments were even more dynamic and complex than our most sophisticated models have presumed. Imagine a mysterious force flickering into existence for a brief cosmic moment, only to vanish without a trace. This is the compelling idea behind early dark energy, a theoretical proposal that offers one of the most elegant solutions to the Hubble tension. To understand how it works, we need to revisit the universe's first few 100,000 years, a period of incredible density and heat that culminated in the release of the cosmic microwave background. Our standard model assumes that the energy density of the cosmos during this time was dominated by a smooth mix of radiation and matter. But what if there was a third fleeting player on the field? Early dark energy, or EDE, proposes exactly that. It suggests that a form of dark energy, similar to the force accelerating the universe today but far more ephemeral, briefly existed before the moment of recombination. This wasn't a constant, enduring presence like its modern counterpart. Instead, it's imagined as a transient field that reached its peak influence around the time the CMB was being formed and then rapidly faded away, becoming negligible shortly thereafter. Its proposed effect, however, was anything but negligible. By adding a significant amount of extra energy density to the universe during this critical window, EDE would have acted like a temporary booster rocket attached to the fabric of spacetime itself. This extra energy would have directly influenced the expansion history. For a short period, the universe would have expanded just a little bit faster than our standard models predict. This subtle change in the expansion rate is the key to unlocking the entire puzzle. Remember the sound horizon scale. That fundamental ruler imprinted on the CMB is determined by how far a sound wave could travel between the Big Bang and recombination. A faster expansion rate during that period means the universe is getting bigger more quickly, which actually shortens the distance those sound waves can cover. Think of it like trying to swim across a river that is suddenly flowing faster. You won't make it as far across before being swept downstream. In this cosmic analogy, the sound waves are the swimmer and the expansion of the universe is the current. With EDE boosting the current, the waves don't travel as far. The sound horizon ruler becomes shorter. Now, let's bring this back to the Planck satellite's measurement. Planck looks at the sky and measures the angular size of those frozen sound waves with incredible precision. It sees that they subtend a certain angle. In the standard model, we think we know the true physical length of the ruler that created those patterns. From the observed angle and the assumed ruler length, we use geometry to calculate the distance to the CMB, which in turn gives us the Hubble constant. But if EDE was real, the ruler was actually shorter than we think. So when Planck sees patterns of a certain angular size, and we now know the ruler that made them was shorter, the only way the geometry works is if the CMB is actually closer to us than we previously calculated. If the object is closer, then the expansion rate needed to put it there must be higher. This elegantly nudges the predicted value of the Hubble constant from the early universe upward, potentially right into the range measured by the local distance ladder. Both measurements could be correct. Our interpretation of the early universe data was simply based on an incomplete model, missing this brief, energetic guess. The beauty of early dark energy is that it primarily affects this one specific epoch, leaving the later evolution of the universe largely untouched. It comes, it boosts, and it vanishes, reconciling the early and late measurements without breaking the many other successful predictions of the standard cosmological model. For scientists, it represents a minimal and compelling adjustment, a single new ingredient that surgically fixes the most glaring problem in modern cosmology. While it remains a theoretical proposal awaiting solid observational evidence, it exemplifies the kind of creative, profound thinking the Hubble tension has inspired, turning a confounding discrepancy into a beacon pointing toward a deeper cosmic history. What if the problem isn't with the contents of the universe, but with the very rules that govern it? This leads us to one of the most radical and thrilling possibilities sparked by the Hubble tension, that our understanding of gravity itself might be incomplete. For over a century, Einstein's theory of general relativity has been the undisputed foundation of cosmology. It describes gravity not as a force, but as the curvature of spacetime itself, warped by mass and energy. Its predictions have been confirmed time and again, from the bending of starlight around the Sun to the precise orbits of Mercury. It is the engine that powers our entire model of the cosmos. But the persistent discrepancy in the Hubble constant is forcing a small but growing number of physicists to ask a heretical question. Could general relativity break down on the largest imaginable scales? This is the world of modified gravity theories, often shortened to MOG. These are not attempts to overthrow Einstein's work, but to extend it, suggesting that the relationship between matter, energy, and the curvature of spacetime might be more complex than we currently know when applied to the entire universe. The central idea is that gravity might behave slightly differently across vast cosmic voids than it does within the relative density of a solar system or a galaxy. If true, this would be a seismic shift in physics, offering a way to explain the accelerating expansion of the universe without the need for a mysterious dark energy, and potentially resolving the Hubble tension in the process. Think of it this way: our standard model uses general relativity as an immutable rulebook to predict how the universe should expand from its initial conditions. The Hubble tension suggests the prediction is wrong. One solution is to add new ingredients to the universe, like early dark energy or weird dark matter. But the other, more profound solution is to propose that we've been using the wrong rulebook all along. Perhaps the equations of gravity need a tiny adjustment term that only becomes significant over billions of light years. This adjustment could mimic the effects of dark energy, causing the expansion to accelerate, but it would do so in a way that changes the relationship between the early universe and the late universe, potentially reconciling the two conflicting measurements. One of the most prominent examples of this approach is a theory known as MOND, or modified Newtonian dynamics, originally proposed to explain the rotation of galaxies without invoking dark matter. Some versions of MOND have been extended to cosmological scales. These models suggest that the strength of gravity doesn't diminish with distance exactly as Newton or Einstein predicted. At extremely low accelerations, which are common in the diffuse outskirts of galaxies and in the vast emptiness between them, gravity might get a tiny bit stronger. This extra gravitational pull could, in some formulations, create an effect that looks like accelerated expansion from our perspective, all without a shred of dark energy. For cosmologists, the appeal of modified gravity is its breathtaking economy. It seeks to solve two of the biggest mysteries in science, dark matter and dark energy, with a single stroke by revising the fundamental force that shapes the cosmos rather than inventing new, undetectable substances. The Hubble tension acts as a critical stress test for these ideas. A successful modified gravity theory wouldn't just explain the acceleration. It would also need to naturally produce a higher value for the Hubble constant from the CMB data, or make the local measurement align better with the early universe prediction. It's a tall order, but the mere fact that such theories are being seriously explored and developed in direct response to this tension speaks to its power as a catalyst for scientific revolution. Of course, modifying gravity is an enormous challenge. General relativity has passed every test thrown at it with flying colors for a century. Any new theory must not only explain the cosmic acceleration and the Hubble tension, but also perfectly reproduce all the successes of Einstein's theory in our solar system and in binary pulsar systems. It's a razor's edge to walk, deviating just enough to fix the big problems without breaking everything that already works. Yet, the stubborn refusal of the Hubble tension to disappear is providing a crucial mathematical target for these theories to aim for. They are no longer just abstract speculations, they are potential solutions to a concrete, observed anomaly. This transforms the field from a philosophical exercise into a rigorous experimental pursuit, where theories can be tested and falsified against the hard data of the cosmos. The tension is, in effect, shining a light on a path that leads beyond Einstein, inviting us to consider that the greatest force in the universe may still have secrets to reveal. This brings us to a number so fundamental, so deeply woven into the fabric of everything we know about the cosmos, that a disagreement over its value isn't just a technical problem, it's a philosophical earthquake. The 12th reason the Hubble tension is so profoundly disorienting is the sheer significance of the Hubble constant itself. This isn't some obscure parameter in a complex equation. It is the master key that unlocks the scale, the age, and the very fate of the entire observable universe. A discrepancy in its value doesn't just mean our math is a little off. It means our most basic comprehension of reality might be fundamentally miscalibrated. Think of the Hubble constant as the ultimate cosmic speedometer. It tells us how many additional kilometers of space are created between us and a distant galaxy every second for every megaparsec of distance. But its importance goes far beyond just measuring current speeds. This number is the linchpin that connects our present moment to the entire history of the cosmos. By measuring how fast the universe is expanding today and then mathematically running that expansion backwards, we can calculate the moment when everything was compressed into a single point, the age of the universe. The value of the Hubble constant is directly and inversely linked to the age of everything. A higher expansion rate means the universe reached its current size faster, implying a younger cosmos. A lower expansion rate suggests a more leisurely, older universe. The 5 or 6 unit gap between the Planck and supernova values translates into a difference of over 1 billion years in the estimated age of the universe. That's not a rounding error, that's a gap longer than the time between the formation of Earth and the appearance of the first complex life. We are disagreeing on the very birthday of existence. Furthermore, the Hubble constant sets the size of our cosmic horizon, the observable universe. The distance to that horizon is determined by how far light has been able to travel since the beginning of time, all while space itself has been stretching. The expansion rate directly dictates that maximum distance we can possibly see. A different Hubble constant doesn't just change the age, it changes the apparent size of our entire cosmic home. It recalibrates the vast distances to every galaxy, every quasar, every filament in the cosmic web. This number is the ruler we use to measure the cosmos, and the tension suggests we might be reading the markings on that ruler incorrectly. This is why the stakes are so astronomically high. Cosmology is a unique science. We cannot rerun the experiment of the universe. We have one set of data, one history to study. The Hubble constant is our primary tool for reconstructing that singular story, from the faint echoes of the Big Bang to the brilliant explosions of modern supernova. It is the through line that connects the first chapter to the last, For this central narrative thread to be frayed, for the story told by the beginning to not match the story told by the ending, creates a deep crisis of confidence. It forces us to confront an unsettling possibility that our entire chronology of the universe, from its fiery birth to its accelerated present, might be built on a foundation that is slightly but significantly cracked. The Hubble tension is more than a puzzle. It is a direct challenge to the timeline of reality itself, leaving us to wonder if we have truly grasped the scale of the cosmos we call home. Just when the problem seemed neatly defined as a conflict between the ancient and the modern cosmos, the plot thickens. The 13th layer of this mystery reveals that the tension isn't just a simple two-sided debate. Even our local, modern measurements can't seem to agree amongst themselves. Within the camp that studies the present-day universe, different teams using different cosmic landmarks are finding their own smaller discrepancies. This isn't just a puzzle, it's a puzzle within a puzzle, suggesting that the complexity of calibrating our cosmic neighborhood is far greater than anyone anticipated. The most famous local measurement comes from the SH0ES team, and collaboration named for the supernova and H for the Hubble Constant. Their result is the one we've been discussing, that value of around 73 kilometers per second per megaparsec, derived from the beautiful chain of Cepheid variables and Type 1, a supernova. For years, this has been the gold standard for the local expansion rate, but another powerful method exists, one that uses a different kind of stellar beacon, the tip of the red giant branch, or TRGB. Red giant stars are common, aging stars that burn helium in their cores. At a very specific point in their evolution, they undergo a well-understood flash of helium ignition that causes them all to reach the same peak brightness. This makes them another fantastic standard candle, a rival to the Cepheids. The teams using the TRGB method have meticulously built their own version of the distance ladder, independent of the Cepheid route. And their result tends to land somewhere in the middle, often around 69 or 70 kilometers per second per megaparsec. It's not as low as the Planck prediction, but it's also not as high as the SH0ES result. This creates a fascinating, smaller tension right here in our own cosmic backyard. Why does this matter so much? It transforms the narrative from a simple clash between two methods into a much richer and more nuanced detective story. If the TRGB and SH0ES results agreed perfectly with each other but both disagreed with Planck, the case for new physics would be incredibly strong. It would suggest a clean break between the early and late universe, but the fact that they don't perfectly agree introduces a critical element of doubt. It forces us to confront an uncomfortable possibility. Maybe our local measurements, as heroic as they are, still harbor hidden, unaccounted for systematic errors that we simply haven't identified yet. The TRGB method has its own set of potential pitfalls and calibrations. For instance, the brightness of the tip of the red giant branch can be very slightly influenced by a star's metal content or age. Teams have to correct for these factors, and even tiny imperfections in those corrections could nudge the final result. This doesn't invalidate the local measurements, it simply highlights the immense difficulty of the task. Measuring the universe is an exercise in mind-boggling precision. We are trying to use stars, which are complex and varied objects, as perfectly uniform light bulbs. The SH0ES team has immense confidence in their Cepheids, while the TRGB teams have equal faith in their red giants. Each method is a masterpiece of astronomical engineering, but they are built on different foundations. Their disagreement is a humbling reminder that we may not yet have a perfect handle on the detailed astrophysics of these stellar candles. It could be that one method is slightly closer to the ultimate truth, or that the truth lies somewhere between them, waiting for an even more precise technique to reveal itself. This small attention acts as a crucial cautionary note, reminding scientists that before we can confidently declare a revolution in physics, we must first be absolutely certain we have eliminated every last speck of cosmic dust from our own instruments and models. The search for that certainty is what drives the field forward, with each team meticulously checking the other's work in a collective effort to solve the greatest cosmic mystery of our time. Yet another layer of this intricate puzzle comes from a seemingly obscure galaxy 23 million light-years away, offering a measurement so geometrically pure it cuts through the astrophysical uncertainties that plague other methods. This is the story of NGC 4258, a spiral galaxy with a supermassive black hole at its heart, surrounded by a whirling disk of gas and dust. Within this disk, nature has provided us with a phenomenon that acts as a natural cosmic rangefinder, water masers. The precision of the distance measured to this single galaxy has become a cornerstone of the modern distance ladder, and its unwavering result only deepens the mystery of the Hubble tension. To understand why this is so important, we need to appreciate the difference between a geometric measurement and the standard candle approach. Cepheid variables and supernovae are standard candles. We infer their distance by comparing their known brightness to how dim they appear. This process, while incredibly refined, still relies on a chain of assumptions and calibrations. A geometric measurement, by contrast, is direct. It uses pure trigonometry, the same way a surveyor measures the distance to a faraway tree by measuring its parallax shift from two different points. Water masers in NGC 4258 allow astronomers to do this on a galactic scale. Masers are like lasers, but for microwave light. They occur when water molecules in dense, hot gas clouds are energized, often by the intense radiation near a black hole, and they emit extremely bright, coherent beams of microwave radiation at a very specific frequency. In NGC 4258, these masers are found in a nearly perfect, thin disk orbiting the central black hole. Because we understand the dynamics of orbits so well, we can use the Doppler shift of the maser light to map the precise rotation of this disk. Masers on the side spinning toward us have their light blue-shifted, while those spinning away are red-shifted. From this, astronomers can construct a stunningly detailed three-dimensional map of the entire maser disk. But the true magic happens with the masers that are located along the line of sight directly toward or away from us at the center of the disk. Their light doesn't show a rotational Doppler shift. Instead, their signals show a distinct, precise drift in frequency over time. This drift is caused by the centripetal acceleration of the gas as it orbits the black hole. By meticulously tracking this acceleration and combining it with the observed angular size of the maser disk on the sky, scientists can perform a direct trigonometric calculation to get the distance. It's a measurement based solely on geometry and fundamental physics, completely independent of the brightness of any star. The result is a distance to NGC 4258 with an uncertainty of just about 3%, a breathtaking feat for an object so far away. This precise distance then becomes a critical anchor point for the entire cosmic distance ladder. Instead of relying solely on the more distant Large Magellanic Cloud to calibrate Cepheid variables, astronomers can use the geometrically measured distance to NGC 4258. They find the Cepheids in that galaxy, measure their periods and apparent brightness, and use the known distance to firmly pin down their true, intrinsic luminosity. This creates a rock-solid foundation for the next step, using those now perfectly calibrated Cepheids to measure the distance to galaxies that have hosted Type 1, a supernova. When this maser-based calibration is fed into the ladder, it consistently reinforces the higher value for the Hubble constant, right around 73 kilometers per second per megaparsec. The power of this measurement lies in its independence. It comes from a completely different branch of physics, radio astronomy, and orbital dynamics than the optical measurements of stars and supernova. That two entirely separate paths, one geometric and one based on standard candles, both converge on the same higher value for the expansion rate, is a formidable argument against systematic error. It suggests that the local measurement is not a fluke or a miscalibration. It is a robust, repeatable result confirmed by multiple lines of evidence. The masers in NGC 4258 act as a silent, unwavering witness, testifying that our measurements of the modern universe are likely correct. This forces the focus back onto the early universe and the fundamental physics that connects it to the present day, strengthening the case that the Hubble tension is not our error, but the universe's way of telling us we are missing a vital piece of its story. But just as we thought we had our methods firmly established, the universe handed us a completely new tool, one born from the most violent collisions imaginable. The 15th reason the Hubble tension is so captivating is the arrival of a revolutionary way to measure cosmic distances, using the ripples in spacetime itself, gravitational wave standard sirens. This technique is so fundamentally different, so detached from the old debates about light and dust and stellar physics, that its early results have sent a thrilling shockwave through the entire field, offering a third, independent path to the Hubble constant and landing squarely in the middle of the debate. To understand why this is such a game-changer, we have to go back to a monumental day in 2017. On August 17th, gravitational wave observatories LIGO and Virgo detected a signal unlike any they had seen before. It was the chirp of two neutron stars, ultra-dense stellar corpses, spiraling inward and finally merging in a cataclysm that shook the very fabric of the universe. This event, named GW170817, was a historic first. For decades, astronomers had relied on light, every wavelength from radio waves to gamma rays, to explore the cosmos. But this was different. This was a direct measurement of gravity, the waveform of the signal, its amplitude, and how its pitch changed over time, told scientists everything they needed to know about the masses of the objects and the strength of the gravitational waves at their source. Crucially, the amplitude of the waves tells you how loud the event was in gravitational terms. And just like with sound, if you know how loud something is at the source, and you measure how faint it is when it reaches you, you can calculate the distance. This is why these events are poetically called standard sirens. They are cosmic noisemakers with a known volume. The beauty of this method is its stunning simplicity and independence. It requires no cosmic distance ladder. There are no rungs to calibrate, no Cepheid variables to find, no concerns about interstellar dust dimming the light. The gravitational wave signal gives you the distance directly, cleanly, and geometrically. But there's one catch. While the waves tell you the distance, they don't tell you the direction or the exact host galaxy. This is where the light comes back in. The incredible follow-up to GW170817 saw telescopes all over the world and in space swing into action, pinpointing the flash of light from the merger in a galaxy called NGC 4993. By identifying the host galaxy, astronomers could then measure its redshift, how fast it is moving away from us due to the expansion of the universe. And just like that, they had both parts of the puzzle, the distance from the gravitational waves and the velocity from the redshift. Putting them together gives you a direct one-step measurement of the Hubble constant. So, where did this pristine new measurement land? Right in the no-man's land between the two entrenched values. The initial result from GW170817 gave a Hubble constant of about 70 kilometers per second per megaparsec. This is tantalizingly, almost perfectly, midway between the Planck value of 67 and the SH0 value of 73. This single event, with its large uncertainty, couldn't resolve the tension, but it powerfully confirmed that the discrepancy is real. It wasn't a fluke of the supernova method or a systematic error in the CMB analysis. Here was a third path built on entirely different physics, seeing the same problem. Since that first detection, more neutron star mergers have been observed, and the combined results continue to sharpen this middle-of-the-road value. With more events, the uncertainty will shrink, and the standard siren method promises to become one of the most powerful tools in cosmology. Its current position, squarely between the two other values, is deeply significant. It suggests that the truth might indeed lie somewhere in the middle, or that the local measurements are slightly high and the early universe predictions are slightly low. It forces every theorist to contend with a third, impartial data point. Proposals for new physics, like early dark energy or modified gravity, must now not only bridge the gap between Planck and sh0es, but also account for where the standard sirens land. This new method doesn't simplify the mystery, it deepens it and enriches it, adding a crucial new voice to the cosmic conversation and assuring us that the Hubble tension is the most real and important puzzle in modern science. This growing web of conflicting evidence leads us to one of the most mind-bending and seemingly impossible consequences of the Hubble tension, a direct challenge to the age of the universe itself. The 16th reason this puzzle is so profound is that it creates a genuine cosmic paradox, where the oldest stars in our galaxy appear to be older than the universe that contains them if the local measurement of the Hubble constant is correct. This isn't just a minor inconsistency, it's a logical impossibility that strikes at the very core of our cosmic timeline. To understand this, we need to see how the Hubble constant and the age of the universe are two sides of the same coin. The calculation is, in principle, beautifully simple. Imagine you are in a car and you know you are currently traveling at a fixed speed. If you want to know how long you've been driving, you would divide the total distance you've traveled by that speed. Cosmologists do the exact same thing with the cosmos. The Hubble constant is the current speed of the universal expansion, and the observable universe represents the total distance traveled since the Big Bang. By inverting the Hubble constant, we get what is known as the Hubble time, a rough estimate of the age of the universe. A higher Hubble constant, meaning a faster current expansion rate, implies it took less time to reach the current size, resulting in a younger cosmos. A lower Hubble constant suggests a slower, more leisurely expansion and an older universe. This is where the tension becomes a full-blown chronological crisis. The local distance ladder measurement, which gives us a Hubble constant of around 73, implies a Hubble time of roughly 13.6 billion years. Now, this Hubble time isn't the precise age because the expansion hasn't been constant. Gravity was slowing it down for billions of years before dark energy started speeding it up. Our full models, which account for this changing rate, put the actual age from the local measurement at about 13.8 billion years. Meanwhile, the Planck measurement of 67.4 leads to a calculated age of about 13.88 billion years. That's a difference of nearly a billion years. While that might not sound like much on a cosmic scale, it becomes everything when we look at the oldest objects in our own celestial backyard. For decades, astronomers have been measuring the ages of the most ancient stars in our galaxy, particularly those found in vast, dense swarms known as globular clusters. These stellar fossils are the Milky Way's first inhabitants, forming from the pristine hydrogen and helium that existed just after the Big Bang. We can determine their ages by studying their color and brightness on what's called a Hertzsprung-Russell diagram. The point where a cluster of stars begins to turn off from the main sequence tells us with remarkable precision how long ago those stars were born. The consistent result from studying countless globular clusters is that the oldest stars are about 13.5 to 13.6 billion years old, with some estimates even pushing toward 13.8. Now let's line up these dates. If the local Hubble constant is correct and the universe is only 13.8 billion years old, that leaves an impossibly narrow window of time for the first stars to form. The Big Bang itself would have happened 13.8 billion years ago. The universe then had to cool enough for atoms to form, for dark matter to clump into halos, for gas to collapse into those halos, and for the very first generations of stars to ignite. This entire complex process of cosmic dawn is thought to have taken several 100 million years. This would force the first stars to have formed when the universe was only 1 or 200 million years old. Yet, the stars we see in globular clusters are not these mythical, truly first-generation stars. They are second-generation stars made from the ashes of those first supernovae. For them to have formed and evolved to the point we see them today, they require more time, not less. The local Hubble constant value puts the universe's age terrifyingly close to, and in some calculations, even younger than the ages of its oldest stars. It's the equivalent of finding a fossilized bone that carbon dates to 100 million years old, but then being told by a different scientific method that the Earth itself is only 90 million years old. It's a logical paradox that simply cannot be. The Planck value, on the other hand, offers a more comfortable timeline. An age of 13.88 billion years provides that crucial extra cushion of nearly a billion years for the universe to go from a hot Big Bang to the formation of the elegant, ancient star clusters we observe today. This is why the age paradox is such a powerful argument in this debate. It's no longer just about reconciling two numbers from different telescopes. It's about reconciling our entire history of the cosmos. The local measurement, if taken alone, creates an impossible reality where the effect, an ancient star, exists before the cause, the universe that birthed it. This paradox forces us to a critical juncture. Either our methods for dating the oldest stars are wildly and systematically incorrect, which decades of stellar astrophysics suggest is highly unlikely, or the local expansion rate is being misinterpreted in a way that makes the universe seem artificially young. More likely, it is the strongest evidence yet that our standard model of cosmology is missing a vital piece, a piece that would not only reconcile the expansion rates but also restore a logical, sequential flow to the very story of time. Moving beyond the ages of individual stars, we can look at the largest structures in the cosmos for more clues. This brings us to the 17th piece of the puzzle, the immense maps of galaxies and voids created by massive sky surveys, which provide a completely different way to measure the universe's expansion. Projects like the Sloan Digital Sky Survey, or SDSS, and the Dark Energy Survey, or DES, have spent decades meticulously charting the positions of millions of galaxies across vast volumes of space. The resulting three-dimensional atlas of the cosmos is more than just a pretty picture. It's a fossil record of how gravity has shaped the universe over billions of years, and it holds its own independent estimate for the Hubble constant. The secret lies in something called Baryon acoustic oscillations, often shortened to BAO. This is a direct descendant of those same sound waves we discussed that were frozen into the cosmic microwave background. Remember the sound horizon scale? That specific distance that pressure waves could travel in the early universe became a standard ruler, permanently imprinted on the distribution of matter. After the CMB was released, that frozen wave pattern acted like a template. Gravity spent the next several billion years pulling matter, both the normal baryonic matter and the dark matter, toward those original dense ripples. This means that galaxies today are not distributed randomly. There is a subtle but statistically powerful tendency for galaxies to be separated by a specific preferred distance, the physical size of that sound horizon ruler, stretched to a colossal scale by the expansion of the universe. This gives astronomers a powerful geometric tool. By measuring the sky for millions of galaxies, they can detect this preferred separation scale. They can see what angle this billion light-year-long ruler subtends on the sky. Just like with the CMB, knowing both the apparent angular size and the true physical length of the ruler allows them to calculate the distance to those galaxies, and from there, the expansion rate of the universe at the time their light was emitted. The beauty of BAO is that it probes the universe at a middle age, not the pristine infant universe of the CMB, and not the local, modern universe of the supernova, but the cosmic adolescence roughly 3 to 7 billion years ago. It's like finding a fossil from a dinosaur rather than a single-cell organism or a modern mammal. It gives us a critical data point from a different evolutionary era. So where does this middle-aged measurement land? Almost perfectly and perplexingly in the middle of the debate. The BAO results from these giant galaxy surveys consistently point to a Hubble constant value of around 68 or 69 kilometers per second per megaparsec. This is significantly higher than the Planck prediction of 67.4, but notably lower than the local supernova value of 73. It doesn't resolve the tension, it deepens it by adding a third, highly respected data point that refuses to side with either camp. This middle ground result is incredibly robust because it relies on pure geometry, the distribution of galaxies in space, rather than the brightness of stars or the physics of the primordial plasma. It's a measurement that is largely immune to the astrophysical systematic errors that plague other methods, like interstellar dust or the complex evolution of stellar populations. This creates a fascinating and confusing narrative across cosmic time. The early universe CMB says one thing, the modern universe supernova says another. And the universe in its middle age BAO whispers something right between them. This progression suggests the tension might not be a simple binary conflict, but evidence of a subtle evolution in the expansion rate that our standard lambda CDM model doesn't predict. Perhaps dark energy's influence wasn't a simple on-off switch but has a more complex history. Or maybe there is an unknown component in the universe that was most influential during these middle billions of years, gently tweaking the expansion in a way that leaves the early and late universes looking out of sync. The large-scale structure of the universe, mapped in such glorious detail, doesn't simplify the mystery. It adds a crucial, complicating, and utterly essential chapter to the story, confirming that the Hubble tension is a thread woven through the entire history of the cosmos. Perhaps the most compelling aspect of this entire mystery is its stubborn refusal to be resolved. Over a decade has passed since the Hubble tension first emerged as more than just a minor curiosity, and in that time it has only grown stronger and more defined. This persistence is the 18th and perhaps most convincing reason that scientists are so captivated. It's the difference between a single strange reading that might be a fluke and a consistent anomaly that sharpens into focus the harder we look, defying every attempt to explain it away. Think of it like a detective meticulously re-examining a crime scene with better and better technology. At first, a blurry photograph might suggest a discrepancy, but it could easily be dismissed as a smudge on the lens or a trick of the light. But what happens when you return with a higher resolution camera, then a forensic scanner, then a DNA sequencer, and that same puzzling detail not only remains but becomes clearer and more pronounced with each new level of scrutiny? You are forced to conclude that the detail is real and your initial understanding of the scene was incomplete. This is precisely what has happened in cosmology. A decade ago, the error bars on both the Planck and supernova measurements were larger. The two values were different, but their margins of uncertainty overlapped slightly, offering a tantalizing hope that better data would bring them together. Instead, the opposite occurred. Research teams on both sides of the divide have been engaged in a relentless campaign of improvement. The SH0ES team, using the Hubble Space Telescope and now supported by the James Webb Space Telescope, has observed more Cepheid variables in more galaxies with more precise calibrations than ever before. They have tightened their error margins to an astonishing degree. Similarly, analysis of the Planck data has been refined and cross-checked against other CMB experiments, squeezing the uncertainty on its prediction down to a fraction of a percent. The result is that the two central values have not budged. They have stayed rock solid, anchored in their separate realities, but the error bars around them have shrunk dramatically, pulling away from each other until there is now a yawning chasm of statistical significance between them. The probability that this discrepancy is due to random chance has plummeted from a few percent to less than 1 in a million. What was once a faint whisper of a problem is now a deafening shout. This persistence transforms the tension from a potential problem of measurement into a robust feature of the universe itself. If it were a simple systematic error, one would expect it to diminish, change, or even vanish as our tools improve and our understanding deepens. The fact that it intensifies is a powerful argument that we are not dealing with a human mistake, but with a fundamental feature of nature that our current models are failing to capture. It's as if the universe is insisting on this discrepancy, demanding that we pay attention. This unwavering signal gives scientists the confidence to pursue more exotic explanations, from early dark energy to modified gravity, because they know they are chasing something real. The tension is no longer a controversy, it is a datum, a solid piece of observational evidence that any complete theory of the universe must now explain. Its enduring presence is the strongest clue we have that we are on the verge of a profound discovery, one that has been honed and sharpened by a decade of the most precise scientific scrutiny in human history. And this brings us to a truly staggering aspect of the Hubble tension, a reason that transforms it from a scientific curiosity into a full-blown crisis: its overwhelming statistical significance. In the world of physics, where certainty is hard-won and claims of discovery are met with intense skepticism, researchers have developed a rigorous standard to separate potential flukes from genuine breakthroughs. This standard is known as the 5 sigma threshold. It's a measure of statistical confidence so high that it is considered the gold standard for announcing a discovery, the same benchmark used to confirm the existence of foundational particles like the Higgs boson. And the Hubble tension has now crossed this monumental threshold, reaching a confidence level that means there is less than a 1 in a million chance that the discrepancy is merely a random fluctuation or a statistical accident. To grasp what this means, imagine flipping a coin. If you flip it 10 times and get 7 heads, you might be a little surprised, but you'd readily accept it as a plausible run of luck. That's a low sigma result. Now imagine flipping that coin thousands of times and consistently getting heads 60% of the time. The probability of that happening by pure chance becomes astronomically small. At the 5 sigma level, the probability is so infinitesimal that it's like correctly predicting the outcome of 20 consecutive coin flips, or like 2 people independently shuffling a deck of cards and ending up with the exact same order. It's a signal that screams that something real and fundamental is happening beneath the surface. This is precisely where we stand with the Hubble tension. The early universe prediction from the Planck satellite and the local measurement from the supernova distance ladder are not just 2 numbers that are a little bit different. Their error bars, the statistical ranges of uncertainty, have been squeezed so tight by years of meticulous observation and analysis that they now sit a vast 5 standard deviations apart. This isn't a finding that can be dismissed or ignored. In any other field of physics, a 5 sigma discrepancy would be immediately hailed as a clear sign of new physics. It would be front-page news heralding a revolution in our understanding. The fact that this same level of confidence now applies to the expansion rate of the entire universe is nothing short of profound. This statistical certainty forces a critical shift in perspective. It moves the conversation from asking if there is a problem to demanding what the problem is. The 1 in a million odds mean that the burden of proof has now flipped. It is no longer the responsibility of those who see the tension to prove it's real. It is now the responsibility of those who wish to uphold the standard model to find the hidden error that could possibly explain it away. And as we've seen, a decade of searching for that error, checking for dust, recalibrating instruments, testing stellar physics, has only made the signal stronger. The 5 sigma significance is the universe's way of shouting over the noise, insisting that our current cosmological model, for all its breathtaking success, is missing a vital piece. It is a beacon of incompleteness, shining with a statistical brilliance that commands the attention of every physicist on the planet, and guarantees that solving this puzzle will be a primary driving force of scientific discovery for years to come. But the plot thickens even further when we realize this isn't an isolated problem. The 20th and perhaps most systematic reason the Hubble tension is so deeply puzzling is that the Hubble constant is not a lone variable in our equations. It is deeply entangled with every other fundamental parameter that describes our universe. Trying to force a resolution by artificially adjusting the expansion rate doesn't just create one problem, it causes the entire elegant structure of our cosmological model to unravel, creating new tensions and inconsistencies elsewhere. This reveals that the issue isn't just with a single number, but with the entire coherent story we tell about the cosmos. Think of our standard cosmological model, lambda cold dark matter, as a perfectly balanced mobile. Each parameter, the Hubble constant, the amount of matter, the density of dark energy, the clumpiness of the universe, is a carefully weighted piece. Tugging on one piece, like the Hubble constant, doesn't happen in isolation. It forces every other piece to shift and readjust to maintain balance. Scientists have tried to do exactly this, to see if they can slightly modify the other parameters to make the early universe prediction yield a higher Hubble constant that agrees with the local measurements. The result is always the same. The model fights back. Forcing a higher H0 from the CMB data immediately throws other precisely measured values into conflict with independent observations, creating a cascade of new problems. A prime example is the matter density of the universe, denoted by the symbol omega m. This parameter describes the total amount of matter, both normal and dark, in the cosmos. Its value has been pinned down with great accuracy by multiple methods, including the large-scale structure of galaxies and, of course, the Planck CMB data itself. The values from these different probes are in beautiful agreement. Now, if you try to force the Planck data to predict a higher Hubble constant, the model compensates by requiring a lower matter density. But this new, lower value for omega m immediately clashes with the robust measurements from galaxy surveys. The universe simply doesn't appear to have less matter than we've measured. You might fix one tension, but you instantly create another, equally severe one. This happens because the parameters in our model are not independent. They are linked through the fundamental equations of gravity and expansion. The specific pattern of fluctuations in the CMB is a fingerprint that encodes all these values simultaneously. Changing one changes the interpretation of the entire fingerprint. A higher expansion rate would mean that the universe evolved more quickly, which would in turn affect how gravity sculpted the cosmic web of galaxies we see today. The observed large-scale structure of the universe acts as a separate, powerful check on our models, and it firmly rejects the new parameter combinations needed to resolve the Hubble tension. This is a clear sign that we are not dealing with a simple calibration error or a mismeasurement of a single quantity. We are facing a fundamental inconsistency in the overall model itself. The mobile cannot be rebalanced with a gentle nudge. Its very structure may need to be reimagined with a new piece or a different set of connections we have not yet discovered. But even if we could perfectly isolate the Hubble expansion from all other motions, we face another layer of complexity right in our own cosmic backyard. The space between galaxies isn't a perfectly smooth, uniform void. It's a dynamic landscape of gravitational pull and push, filled with rivers of galaxies flowing en masse toward the densest concentrations of matter. When we try to measure the Hubble constant locally, we are not just measuring a clean, universal expansion. We are trying to pick out that single signal from a symphony of other motions, all superimposed on top of it. This is the challenge of peculiar velocities, and it represents a significant, though likely insufficient, hurdle in our quest to pin down the true value of H0. Every galaxy has two types of motion: The first is the Hubble flow, the relentless, smooth stretching of space itself that carries galaxies away from each other. This is the motion we want to measure. The second is its peculiar velocity, any additional motion caused by the local gravitational tug of war. Our Milky Way, for instance, is being pulled toward the immense gravitational attractor of the Great Attractor and the even larger Laniakea supercluster. The Andromeda Galaxy is not simply receding from us due to the expansion. It is also hurtling towards us for a future collision, its peculiar velocity completely overwhelming the Hubble flow at that close distance. For more distant galaxies, these peculiar motions are smaller relative to the expansion, but they are never zero. When we measure a galaxy's redshift, we are measuring the combined effect of its recession due to the expansion of the universe and its own peculiar motion toward or away from us. To get the true Hubble flow, we must find a way to subtract that local component. This is an immense statistical challenge. To correct for these effects, cosmologists map the local universe in incredible 3D detail, using surveys to chart the positions and distances of thousands of galaxies. They then use sophisticated computer models to map the expected gravitational pulls from all the nearby superclusters and voids, predicting how those tugs should influence the motions of galaxies in our region. This allows them to estimate and subtract the peculiar velocity component from the observed redshift, leaving behind, in theory, a cleaner measurement of the pure Hubble flow. The process is like trying to measure the steady, global wind speed while standing in a city with buildings that create their own complex gusts and downdrafts. You need a detailed map of every street and skyscraper to understand and correct for the local wind effects to find the underlying atmospheric current. Critics of the local measurement have wondered if we've somehow misjudged the scale of these local flows. Could our entire galactic neighborhood be part of a much larger, faster, dark flow or bulk motion that is skewing our measurements, making the local expansion appear faster than it truly is on a truly cosmic scale? It's a fascinating thought. However, while these corrections are complex and absolutely essential, the consensus among researchers is that they are not nearly large enough to account for the full 5 or 6 unit discrepancy in the Hubble constant. The teams behind the SH0ES results have incorporated detailed models of these peculiar velocity fields into their analysis. They have found that while the corrections are important and do shift the results slightly, they cannot explain away the tension. The higher value for H0 persists even after meticulously accounting for the gravitational influence of every known cluster and supercluster in our vicinity. Furthermore, the local measurement isn't based on a single galaxy or a single direction. It uses a vast number of supernovae spread across the sky and at different distances. Any large-scale bulk flow would affect galaxies in a specific direction in a coordinated way. The fact that the high expansion rate is consistently measured in many different directions acts as a powerful argument against a local velocity anomaly being the primary culprit. The peculiar velocity problem is a classic example of a systematic error that has been thoroughly investigated, quantified, and largely ruled out as the root cause. It reminds us of the incredible care required to measure the cosmos, but it also strengthens the case that the tension we are seeing is not born from a local illusion, but from a genuine, fundamental disagreement between the modern universe and the ancient one. Perhaps the most exciting aspect of this entire cosmic puzzle is the sheer possibility it represents for the future of cosmology itself. We are not just talking about adjusting a number in a textbook. We are standing at the precipice of a potential revolution that could redefine our understanding of the fundamental laws that govern everything from the smallest particles to the grandest structures in the universe. Resolving the Hubble tension is not a matter of simply choosing a winner between two competing measurements. It is a guaranteed path to profound new knowledge, a path that leads to one of two transformative outcomes, each with the power to reshape science for generations to come. On one hand, the solution could be a breathtaking discovery of new physics. Imagine the moment when a team of researchers, perhaps analyzing data from the James Webb Space Telescope or the next generation of gravitational wave observatories, uncovers irrefutable evidence for an ingredient missing from our cosmic recipe. It could be the confirmation of early dark energy, a fleeting field that gave the infant universe an extra push. It could be the detection of a new property of dark matter, showing it can interact with itself in ways we never dreamed. Or it could be something even more radical, like a modification to Einstein's theory of gravity that holds true on the largest scales. A discovery of this magnitude would be an epoch-making event, a paradigm shift comparable to the realization that the universe is expanding or that dark energy exists. It would instantly open up vast new fields of theoretical and experimental research, answering one monumental question while posing a dozen more fascinating ones. The scientists at the forefront of this breakthrough would undoubtedly be contenders for the highest scientific honors, their names etched alongside Hubble, Einstein, and Penzias and Wilson for revealing a deeper layer of cosmic truth. On the other hand, the resolution could come from a stroke of brilliant, meticulous detective work that identifies a hidden systematic error. This might sound like a less glamorous outcome, but in many ways it would be an equally powerful testament to the scientific process. It would mean that after over a decade of scrutiny by thousands of the world's brightest minds, someone finally found the proverbial speck of dust on the lens, a subtle calibration error in a telescope, a minor misunderstanding in the physics of supernova or Cepheid variables, or a complex statistical artifact that had eluded everyone. Uncovering such a flaw would require a deep, profound insight. It would be a monumental achievement in precision and skepticism, demonstrating the incredible self-correcting mechanism of science. It would not diminish the field but would instead strengthen it, reinforcing our confidence in the standard model of cosmology and solidifying our understanding of the universe. The individual or team who solved it would be hailed for their clarity and rigor, having resolved the most nagging anomaly in modern astronomy and assured us that our foundational theories are on rock-solid ground. Regardless of which path proves correct, the journey to get there is already transforming cosmology. The Hubble tension has acted like a powerful magnet, pulling resources, talent, and technological innovation toward this single goal. It has spurred the development of breathtaking new telescopes and missions, like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, which are specifically designed to deliver the precise data needed to crack this case. It has fostered unprecedented collaboration between particle physicists, astronomers, and theoreticians, breaking down the silos between disciplines in a unified quest for answers. This tension is more than just a problem. It is a catalyst accelerating the pace of discovery and ensuring that the coming decade will be one of the most exciting in the history of our study of the cosmos. The resolution, when it finally comes, will not just be an endpoint. It will be a new beginning, launching us into the next chapter of our eternal attempt to understand the universe and our place within it. Now we journey to a pivotal but shadowy chapter in the cosmic story, a period known as the Epoch of Reionization. This was the universe's Great Awakening, a transformative era that occurred hundreds of millions of years after the Big Bang, when the first stars and galaxies ignited, flooding the cosmos with their brilliant, energetic light. For eons, the universe had been dark and neutral. The hydrogen gas that filled all of space was calm and opaque, its atoms whole. But the birth of those first massive stars changed everything. They poured out intense ultraviolet radiation, which proceeded to strip electrons away from the neutral hydrogen atoms, reionizing the gas and slowly turning the entire universe transparent again. This process didn't happen instantly. It was a gradual, patchy dawn, with bubbles of ionized plasma growing around the first light sources until they eventually overlapped and filled all of space. Understanding this complex transition is critical because the way it unfolded leaves a subtle imprint on the oldest light we see, the cosmic microwave background, and our uncertainty about its details could be secretly influencing the Hubble tension. To see how this connects, we need to return to the Planck satellite's measurement. The CMB is a snapshot from the moment the universe first became transparent at the time of recombination. But that light didn't travel to us completely unimpeded. During its nearly 14 billion-year journey, it passed through the entire history of the universe, including the epoch of reionization. As those CMB photons encountered the newly freed electrons within the ionized bubbles, they could scatter off them, much like a car's headlights scattering in a fog. This later scattering doesn't erase the primordial pattern from the Big Bang, but it does subtly blur it. It dampens the amplitude of the temperature fluctuations we observe, particularly on smaller, finer scales. Think of it as looking at a pristine fossil through a slightly frosted glass pane. The overall shape is still clear, but the finest details are softened. The Planck team's analysis must account for this reionization blurring to accurately extract the true, initial conditions of the universe. They do this by including a parameter that describes the total optical depth caused by this electron scattering, denoted by the Greek letter tau. This is where the uncertainty creeps in and potentially ties into the Hubble constant dispute. The value of tau is not something Planck can measure with the same exquisite precision as the other parameters. It has a larger margin of error. This optical depth is fundamentally linked to the timing and duration of reionization. If reionization happened earlier and more quickly, it would imply a higher optical depth, as the CMB light would have had more free electrons to scatter off of throughout its journey. A higher tau value, when fed into the cosmological model, actually leads to a slightly higher predicted value for the Hubble constant from the CMB data. It's a small effect, but in a discrepancy where every decimal point counts, it becomes significant. The current best fit value from Planck suggests reionization was a relatively late process, peaking around 550 million years after the Big Bang, and this points toward the lower Hubble constant. However, if new evidence were to show that reionization actually began significantly earlier, perhaps due to more efficient or numerous early galaxies than we currently model, it would require a higher tau. This would, in turn, nudge the early universe prediction for the Hubble constant upward, potentially closing a portion of the gap with the local measurements. Intriguingly, observations from the James Webb Space Telescope are now peering directly into this era, revealing the very first galaxies in stunning detail. Some of these initial findings suggest that early galaxies might have been more numerous and brighter than many cosmological simulations predicted. If this holds true, it could mean that reionization started earlier and proceeded more aggressively. This wouldn't single-handedly resolve the entire Hubble tension, but it could account for a meaningful fraction of the difference, suggesting that part of the problem may simply be an incomplete understanding of this specific, complex chapter in our universe's history. It transforms the epoch of reionization from a fixed backdrop into an active variable, a period of cosmic change whose details we are still piecing together, and whose final story may hold a key to harmonizing the two conflicting tales of our expanding universe. But to truly break the deadlock, we need more than just a new instrument. We need a new way of seeing the universe altogether. This brings us to the transformative promise of multi-messenger astronomy, a field that doesn't just look at the cosmos but listens to it, feels its vibrations, and detects its ghostly particles all simultaneously. For centuries, astronomy was the science of light. We built ever larger telescopes to collect photons from across the electromagnetic spectrum, from radio waves to gamma rays. But light can be dimmed, distorted, or obscured. The universe, we are learning, broadcasts its most dramatic events on multiple channels, and by tuning into all of them at once, we gain a complete, unambiguous picture that no single messenger can provide. This holistic approach is our greatest hope for cutting the Gordian knot of the Hubble tension, because it allows us to witness cosmic collisions with a clarity and precision that feels almost like being there. The historic detection of the neutron-star merger GW170817 was a spectacular preview of this power. For the first time, we felt the ripples in space-time from the violent collision, and then, within hours, telescopes around the world swiveled to see the brilliant glow of the resulting kilonova explosion. That single event provided a direct gravitational wave distance and an optical identification for the host galaxy, yielding a single precious data point for the Hubble Constant. But it was just a glimpse. The future of multi-messenger astronomy lies in moving from these rare, singular events to a rich catalogue of them. Next-generation gravitational wave observatories, like the Laser Interferometer Space Antenna, or LISA, which will launch in the next decade, will be sensitive to a much wider range of cosmic events, from the mergers of massive black holes to the subtle hum of binary white dwarf systems. By being in space, free from the seismic noise of Earth, LISA will open a new window onto the low-frequency gravitational wave universe, detecting signals from across the entire cosmos with unparalleled fidelity. At the same time, a new fleet of immensely powerful optical telescopes is coming online. The Vera-C Rubin Observatory, with its gargantuan 3.2 gigapixel camera, will scan the entire visible sky every few nights, automatically alerting astronomers to any change or transient event. It is expected to discover millions of supernovae and countless other variable objects. When a gravitational wave detector like LISA or its Earth-based successors triggers an alert, Rubin and other telescopes will be able to pinpoint the optical counterpart with breathtaking speed and accuracy. But the real power of multi-messenger astronomy goes beyond just light and gravity. The third crucial messenger is the neutrino, an almost massless particle that flies straight out of the heart of these cataclysms without being deflected or delayed. Gigantic neutrino detectors like Ice Cube buried deep in the Antarctic ice and the upcoming cubic kilometer neutrino telescope, or KM3 in the Mediterranean Sea, are designed to catch these elusive particles. When a neutrino arrives at the same time as a gravitational wave and a flash of light from the same patch of sky, it acts as the ultimate stamp of authenticity, confirming the event's origin and nature beyond any doubt. This triangulation of information is what will deliver the pristine, independent measurement of the Hubble constant we so desperately need. A gravitational wave signal gives a direct, absolute distance. The identified host galaxy provides a redshift, and the light and neutrinos tell us exactly what kind of event caused the signal, allowing for precise corrections and removing astrophysical uncertainties. With dozens and eventually hundreds of these standard siren events spread across different distances and directions, we will be able to construct a brand new cosmic distance ladder, one built not on the assumed properties of stars, but on the immutable laws of gravity and geometry. This will allow us to measure the expansion rate not just at a single point in time, but as a function of cosmic history, tracing the evolution of the Hubble constant over billions of years. The resulting data set will be the final arbiter of the tension. It will either definitively confirm the higher local value, shattering our standard cosmological model and forcing a dramatic revision of physics, or it will side with the lower early universe prediction, revealing a subtle, previously unknown systematic error in our measurements of Cepheids and supernovae. Or, in the most thrilling possible outcome, it could paint a more complex picture altogether, showing that the expansion rate has a richer history than we ever imagined, perhaps due to an evolution in dark energy that has left its imprint across cosmic time. Multi-messenger astronomy is not just another tool, it is a paradigm shift. It is our best hope for moving beyond conflicting interpretations and arriving at a direct, undeniable truth about the expansion of our universe, finally answering the question that has defined a generation of cosmology. And so we arrive at the final and perhaps most profound reason the Hubble tension captivates and puzzles scientists. Beyond the numbers, the equations, and the cutting-edge technology, this mystery strikes at the very heart of the scientific endeavor. It serves as a powerful and humbling reminder that our most elegant models of the universe, no matter how successful, are ultimately approximations, beautiful, powerful, but incomplete sketches of a reality far more complex and wondrous than we can imagine. This isn't a failure of science, it is its greatest strength. The entire history of cosmology is a story of building a more perfect understanding, of replacing a good theory with a better one, and the Hubble tension is the latest and clearest signal that we are on the cusp of the next great leap. For centuries, we believed we lived in a static, eternal universe until Edwin Hubble's observations revealed the cosmos was expanding. Then, we thought that expansion must be slowing down until the shocking discovery of dark energy showed it was actually accelerating. At every turn, just when we think we have the final picture, the universe reveals a new layer of complexity. The Hubble tension is the current embodiment of this beautiful, relentless process. It is the universe politely but firmly tapping us on the shoulder and saying, "You're getting closer, but you're not quite there yet." This humility is not a cause for despair, but for exhilaration. It means there is still more to discover, deeper truths to uncover, and that the ultimate adventure of understanding is far from over. This tension, therefore, is more than just a technical problem to be solved. It is a philosophical touchstone. It underscores a fundamental truth about our place in the cosmos. We are not passive observers simply reading off answers from a pre-written cosmic ledger. We are active participants in a grand dialogue with nature, proposing ideas through our theories and listening for a response through our telescopes. The Hubble tension is nature's unambiguous reply to our current best model, a clear message that our questions must become more nuanced, our models more sophisticated. It drives the relentless, passionate pursuit of a more complete story of cosmic evolution, a story that will inevitably include elements we have not yet even dreamed of. It guarantees that the most exciting chapters in our understanding of the universe are not behind us in textbooks, but ahead of us, waiting in the darkness to be illuminated by the next generation of curious minds daring to ask, what if we're missing something? This isn't a puzzle to be feared. It is the very engine of discovery, the signal that we are alive at a moment of genuine revolution, and the invitation to step forward into a deeper, more mysterious, and more magnificent reality. From the profound split between the ancient and modern cosmos to the tantalizing whispers of new physics, from the ghostly influence of neutrinos to the cosmic paradox of stars older than the universe itself, we've journeyed through 25 compelling reasons why the Hubble tension stands as the most captivating puzzle in modern science. This isn't a simple disagreement over a number, it's a multifaceted mystery that touches every corner of astrophysics. It involves the painstaking precision of measurement techniques, from the cosmic distance ladder to the geometry of water mazes. It hinges on our understanding of astrophysical objects, from the rhythmic pulse of Cepheid variable stars to the brilliant, standardized explosions of supernovae. And most thrillingly, it probes the very foundations of fundamental physics and cosmology itself, challenging our models of dark energy, dark matter, and even the laws of gravity as described by Einstein. Each layer of this mystery reveals just how interconnected our universe truly is. A discrepancy in the expansion rate isn't an isolated issue. It sends ripples through everything we think we know, from the universe's birthday to the way its largest structures form. The relentless persistence of this tension, its rise to a 5 sigma level of statistical significance, and its refusal to be solved by simply tweaking other parameters all point to one exhilarating conclusion. We are on the verge of a monumental discovery. This is the living, breathing process of science in its most dramatic form, not a set of stale facts in a textbook, but a dynamic, ongoing detective story where the next clue could come from a gravitational wave observatory, the James Webb Space Telescope, or a brilliant theorist's chalkboard. This story is far from over. Major observatories and brilliant minds around the world are dedicated to cracking this case. The next few years promise more data, more insights, and perhaps finally, a resolution that will redefine our cosmic narrative. We want you to be a part of this journey. What do you think is the most likely solution? Is it a new type of dark energy, a strange property of dark matter, or something even more extraordinary that we haven't yet conceived? Share your own theories and questions in the comments below. We love diving into these discussions with you. If you're as fascinated by the secrets of the cosmos as we are, make sure to subscribe and hit the bell so you don't miss our next deep dive into the mysteries of space, time, and reality itself.